All right. So next we look at multi-qubit gates. Why is this thing not going? I just want this to minimize. Okay, good. So we will be looking at multi-qubit gates now. Multi-qubit gates. But even with multi-qubit gates, we'll be mainly looking at two-qubit gates, because two-qubit gates combined with single qubit gates are more than sufficient for most of the quantum computation tasks. Okay. The most important two-qubit gate is something called C0 gate or control NOT gate. In short, it is written as C0. And the way it acts is the following. When we, it's also called CX. So CX. You will see in a moment why it is called so. So it is a two-qubit gate, and that's why it would now act on two qubits. So let's say 0, 0. But before that, I think, give you an idea of how these two-qubit gates work and what are two-qubit systems. So for single qubits, the basis states are 0 and 1, right? So whatever gate we apply, we try to see how these gates are changing state 0 and state 1. For two qubits, we look at the two qubit basis, which is formed by 0, 0, 0, 1, 1, 0, and 1, 1. That means any two qubit state can be written as a combination of this. So like we used to say, for a single qubit state, the most general single qubit state used to be alpha 0 plus beta 1, right? This is the single qubit state. The most, so I just put a 1 here. The most general two qubit state can be something like A times 0, 0 plus B times 0, 1 plus C times 1, 0 plus D times 1, 1. Okay. So A, B, C, D determines the coefficients of the four basis states 0, 0, 0, 1, 1, 0, and 1. And that's why to know the action of a two qubit gate, we need to know how it acts on 0, 0, 0, 1, 1, 0, and 1, 1 basis states. Similarly, the two qubit gate will have a structure, the metric structure of two qubit gate will be a 4x4 matrix, because the qubits now will have the 4x1 structure. What I mean is 0, 0 would be this factor 1, 0, 0, 0. 0, 1 will be 0, 1, 0, 0. 1, 0 would be 0, 0, 1, 0. And the last one, 1, 1 would be 0, 0, 0, 1. So since the vectors of these basis states are 4x1, we need a 4x4 matrix to apply on two qubit gates. Okay. All right. So I'll just keep this aside and come back to C00. So when C0 applies to 0, 0 basis states, it does nothing. When C0 applies to 0, 1, then also it does nothing. When C0 applies to 1, 0, it makes it 1, 1. And when C0 is applied to 1, 1, it makes it 1, 0. And this is basically the action of C0 gate, and this is how we define C0 gate. So we can say that this is the definition. So the definition of any quantum gate is based on how it operates on the basis states 0 and 1 if it is single qubit, and on the basis states 0, 0, 0, 1, 1, 0, and 1, 1 if it is a 2-qubit gate. So let's look a bit deeper. What is really happening? What's happening is the following. It is called control knot in the sense that we have now 2 qubits. Okay. The first qubit is called as the control qubit, and the second qubit is called as the target qubit. So here I have drawn 2 qubit lines, and for the control we put a dot like this, and on the target qubit we put a symbol which defines the action on the target qubit. So for C0 gate, what happens whenever the control qubit is 0, it operates X gate on the target qubit. Okay, so whenever the control qubit is 1, it operates X gate on target qubit. So there are two aspects here. First, we need to look at the control qubit if it is in state 1 or 0. If the control qubit is in state 0, it will do nothing. For example, here we see the control qubit is 0. Here also the control qubit is 0, and that's why nothing is happening to this state. Okay, they are staying as it is. But for the case where the control qubit is 1, we see that an X gate is applied to the second qubit, the target qubit. So X gate applied to 0 here makes it 1, and X gate applied to 1 here, making it 0. Okay, so this is how control gate in general works. So we can have any kind of general control gate. For example, we can have a control U gate, and that would be something like this. So whenever the first qubit would be 1, it would apply a U gate, which could be anything, on the target qubit. For the C0 gate, we can say C0 gate is a special case of control U gate, where U gate is X gate or NOT gate. And you realize that this is nothing but the symbol of X gate, right? Okay, so let's see how this happens in our IBM Quantum Composer. Okay, so both our qubits are now in state 0. Let's say we are talking about Q of 0 and Q of 1. So this is the control NOT gate, and now I put it here. Okay, so we can see that the state is now at 0, 0. Now we should look at 2 qubits together. So what I'm telling is now we should look at 2 qubits. So these are 4, right? And these 4 represent to the 4 qubit line server. Now we are talking about 2 qubit system. So we'll see what is happening to the first 2 qubits. Okay, nothing is happening if the first qubit is 0 and second qubit is also 0. What happens when the first qubit is 0 and second qubit is 1? So to make the second qubit 1, I'm putting an X gate here. Oops. X gate. Yeah. So you see that, okay, maybe first I should delete it just to avoid the confusion. Okay. So we see that now it is a 0, 1 state, right? The first qubit is in state 0 and the second qubit changes to state 1, and that is this state 0 and 1, 0 and 1. So we expect that this state doesn't change I mean, as well as this state, nothing should happen when I apply the control NOT gate. Yeah, so we see that nothing is happening. It stays the same, right? Okay, so 0, 0 and 0, 1 are done. Now we see what is happening if we apply the state to 1, 0. But to prepare 1, 0, first I should apply this NOT gate to qubit, the first qubit here, right? And I expect this probability distribution to be here because this denotes 1, 0 state, right? So let's go there. And yeah, here it is 1, 0. Now, as we have seen already, for 1, 0, where is it? Yeah, it should take, the state should become 1, 1. Let's see if that's the case. So we apply now control NOT gate. And yeah, indeed the case. We see it becoming 1, 1, right? And here it is also 1, 1. And see that there is no phase getting involved. The phase is same. The phase is 0 always. But just in few moments from now, we'll see another control gate where, the phase would matter. Okay. And so we have seen the action of control NOT gate on 3 states, 0, 0, 0, 1, and 1, 0. Now we remain with the last basis state, that is 1, 1. And to do that, I'm just going to erase this. So let's see how the 1, 1 state should look. The 1, 1 state is this, right? This is the 1, 1 state. So I expect this to jump over here. So here's my 1, 1 state. Yeah, so it jumped over here. So I have now my 1, 1 state. Now I apply the control NOT gate here. Yeah, you'll see that the state indeed became 1, 0, right? This is 1, 0 state. So this is what even we expected, right? 1, 1 becoming 1, 0. So this was control NOT gate acting on the 4 basis states 0, 0, 0, 1, 1, 0, and 1, 1. All right. We should also have a look here, here that this is the edit operation. This is info. So the info shows also how C0 gate is operating. So you could read about it here. And this is, just showing this definition here. This means, I guess it would copy it. What is this? Okay, this basically deletes. All right. What I want to do, what happens if we change the control qubit to something else? What I mean, here the control qubit is the first qubit, that is Q of 0. And the target qubit is the second qubit, Q of 1. Yeah, so there might be a case where we take the second qubit as the control and the first qubit is the target. Okay. And in that case, we would just like to flip it, right? So how to do that? Yeah, we can do that here. So what I can do, I can make now my control 1 as the Q of 1 as the control qubit and Q of 0 as the target qubit. So this is also a possibility, right? And you can see how it would change the qubits. It's straightforward. You apply the same logic, how it would act on 0, 0, 0, 1, 1, 0, and 1, 1 state. Okay, so the control and target qubit you could choose depending upon your need. That's one thing. All right. Just a second. So this is how control NOT gate operates. We can choose the control and we can choose the control and target qubit. Okay. So this is our first control gate. Let's look at the second control gate, and that is the control Z gate. Yeah. So now we'll look at control Z gate. Z gate. I think people also prefer writing just control and not controlled, but I mean, you could write anything that you want. Okay, so how does control Z get operates? Uh, so this is written as CZ in short. So the way it operates is the following. It takes 00 to 00 only, 01 to 01, 10 to 10, and 11 to -11. Okay. So the action here is again on the target qubit, and the target qubit is changing only when the control qubit is 1. But then the change essential is Z gate being operated onto the target qubit. So what it does is, uh, whenever the control qubit is 1, it operates a Z gate on the target qubit. That's why control Z. So essentially, it should have a symbol of this. And I think in some circuits they use this symbol, but you would more commonly see this symbol. Yeah, even in IBM Quantum Composer, we'll have a look at it now. Yeah. Yeah, and that's why we see, even though that's why we see 10 staying intact, because even though the first qubit is state 1, first qubit is in state 1, second qubit is 0, and Z gate applied to 0, just do nothing, right? But then in the fourth case, Z gate applies to 1, and it makes it -1. All right, let's see. So we delete all the states. We apply control Z. Okay, where's control Z? Do we have a control Z here? This is swap gate, right? And this is swap gate. So we don't have a control Z gate here. So what we can do, we can construct a Z gate. We can construct a control Z gate using C0 gate. And the idea is the following. Okay, we'll go to construction of control Z gate in a moment, and verify the action on the basis states. But before that, let's just try to write the matrix structures of these gates. So control, okay, let me go here. So control X gate or control NOT gate will have the following matrix structure. It has to be a 4x4 matrix. And you remember, right? The first column depicts the action on the first qubit. I mean, the output on the first qubit. The second column depicts the action on the second basis qubit. The third column would depict, following the same reasoning, the action on the third qubit, and the fourth column would depict the action on the fourth qubit. So Cx, when operated on 00, it gives 00 only. Cx when operates on 01, it gives 01 only. Cx when operates on 10, it gives 11. And Cx when operates on the final basis state, that is 11, it gives a 10. That's why these columns would take the following. For 00, we get this. For 01, we get this. For 11, we get this. And for 10, we get 1, 0, right? And you could also see that this is indeed nothing but there is a identity gate. It's better to write like this. And then there is a X gate, right? And here we have 0, 0. So this is the matrix structure of X gate, control X gate, sorry. Similarly, for we can construct it for control Z gate, and we'll follow the same reasoning. So the first qubit should be the output when CZ gate operates on 0, 0, right? So the first column should be the output when CZ gate operates on 0, 0. So this should be 0, 0. 0, 1 should be taken to 0, 1. 1, 0 should be taken to 1, 0. But 1, 1 is taken to minus 1, 1, right? That's why the first column should be this. The second column should be this. The third column stays 1, 0. But the final column stays, there should be a minus 1. And I can also write it as identity and then Z gate, because we see that just in case this thing here is X gate and this thing here is Z gate. Okay, and here we'll have 0, 0. Okay, in a similar fashion, the control U gate, I mean this gate, should have the following form. Then it should be a identity matrix and then a U matrix and 0, 0. Overall, it should be a 4 cross 4 matrix, and the CX and CZ are also 4 cross 4 matrix. Okay, so these are the two important uh, control gates. So we saw control X gate and we saw control Z gate. We still could not see the action of control Z gate in IBM Quantum platform, and we'll get back there in a moment. But before that, I would just like to mention some identities which you can check, and I think they are important single qubit identities. So I'll just mention some single qubit gate identities. They will be indeed fun to check on IBM Quantum Composer platform, and that's the reason I'm telling you this. So you could check that if you first apply H gate, then X gate, and then H dagger. So what do I mean by H dagger? H dagger, in fact, is just same as H. Okay, so you could check. I mean, the action of dagger. So what dagger does is it takes the conjugate and then it takes the transpose, right? So H dagger to be Z. So you can check, that the action of H dagger on the basis state is similar to the action of Z. Then H dagger is X, and H dagger is minus Y. Similarly, we have already seen S square equals to Z, yeah, but I'll just write it once more. S square equals to Z, T square equals to S. And we can also see that SX, S dagger is Y, S dagger is minus X. We should also look at how, so these identities denote how, H would transform X, how H would transform G, how a set of gates transform another set of gates. So we can see how T is transforming X, Y, and Z here. So T, when applied to T gate, it gives us a superposition of X and Y gate. When applied to Y gate, it gives me superposition of Y minus X by root 2. And when it applies to Z gate, it gives Z gate. So it does nothing to Z gate. Maybe I missed another. S gate. Applies to this. It does nothing to Z gate. Okay. And decent. Yeah. So S and T gate doing nothing to Z can also be linked to this facts. This facts. Okay. All right. These are some single qubit gates that can be checked. And maybe I'll just briefly check the first identity. H X H dagger equals to Z. But before that, let's prove that H dagger equals to H. I'm sure you can do it already, but just for the sake of completion. So H equals to 1 by root 2, 1, 1, 1 minus 1, right? And there is all the matrix elements are real here. So if I take the conjugate, it stays the same. And then if I take the transpose, then also it stays the same. That's why H is H dagger. And this is the reason we can write H X H dagger to be H X H. And we want to see that this is same as applying Z gate. Okay. So we know that the action of Z gate on 0 is 0, but the action of Z gate on 1 is -1. So let's see if H X H does the same thing. So we first apply H, then we apply X. So we see that before, just because of H and X, we are seeing this double superposition. Sorry, the superposition of these two states. But then I expect when I apply another H gate, it should go back to the state 0. So this superposition probability should vanish. Let's see. Yeah, and that is the case. So at least with qubit 0, H X H does the uh, uh, H X H gate is just equivalent to Z. Now we want to see its action on state 1. Okay. Yeah. And yes, we see that the phase is changing to pi, but the state is staying at 1. So it becomes -1 state, right? And this is how we can confirm that H X H dagger or H X H is just equals to Z. All right. Then it's time we should go to 2-qubit gate identity. And 2-qubit gate identities will help us to emulate the behavior of control Z gate using control NOT gate in IBM Quantum Composer. 2-qubit gate identities. I'll only give the example of the most common ones. And the two most common are this. There is a transformation of control NOT and control Z gate using Hadamard gate. So a control NOT gate is equivalent to applying a Hadamard gate to the second qubit and then applying a control Z gate, keeping the first qubit as the control and the second qubit as the target, and then another Hadamard gate to the second qubit. There's an equivalent identity, which you might guess already, that if I want to construct now CZ gate from control NOT gate, then it is in a similar way can be done by sandwiching a control NOT gate between two head mod gates. Okay. Now okay, this is the control here. All right. So let's see if we can use this circuit, okay, to synthesize control Z gate. Okay. So here it is. But then we need the head mod gate in the second qubit, right? We need two head mod gate in the second qubit and a C0 gate sandwiching between these two head mod gates. Yeah. So this should do the action of control Z gate. That means it should do nothing to state 0, 0. So the initial state was state 0, 0, right? Maybe I can use this partitions here. Is it working? Oh, never mind. Yeah. So what we are trying to do, we are trying to see if this circuit is equivalent to control Z. Okay. So we should check the behavior of the action of these three gates on 0, 0, 0, 1, 1, 0, and 1, 1. Now it's acting on state 0, 0, and we see there's nothing happening. So 0, 0, that's good. What happens when we are applying it on state 0, 1? So now it becomes state 0, 1, right? State 0, 1, right? Because I can put this here just to distinguish that this is my control Z circuit. So for 0, 1, there's nothing happening. 0, 1 is this, right? For 1, 0 also, nothing should happen. So 1, 0 should stay as 1, 0. And we see 1, 0 is staying as 1, 0. And for 1, 1, we should see a phase of how much? Pi, right? So 1, 1 should change to minus 1, 1. So it would again be at 1, 1 here, but here we would see a red color, line. So let's make it 1, 1. And yeah, now you see 1, 1. I mean, here it is 1, 1 with a phase of pi. So 1, 1, this is minus 1. And this confirms that we can use this circuit to implement control Z gate. Okay. So these are some qubit gate identities, right? Single qubit gate and control qubit gates. So we looked at some single qubit gates, some multi-qubit gates, how we can prove circuit identities on IBM Quantum Composer. Next, we want to see how we can use these gates that we have already constructed to generate quantum entanglement. All right. So I'll delete it here for the time being. Okay. So in the next part, we look at quantum entanglement, quantum entangling circuit. And the way you can create entanglement is the following. Firstly, you have to take two qubits because entanglement will only happen between some qubits, right? So you can't do entanglement with just one qubit. You need to have another. So if we start with two qubit, both initiated in state 0, and then we apply Hadamard gate to qubit, the first qubit, and then we apply a control X gate. Oops. to the second qubit. Then in the output, we'll see an entangled state. And why do I say so? I say it because of the following reason. Let's see how this is getting operated. So the gate that is applied first, applied first, here it is H, will operate first, and then the second gate would operate. Okay. So when I write it mathematically, it would be something like this. So the state is 0, 0, and then Hadamard is operating on the first qubit, and after that, C naught, or I write CX, C naught. C naught is operating from qubit 1 to qubit 2. Okay. This is also equivalent to writing C naught gate applies from qubit 1 to qubit 2, and then Hadamard cross identity is applied. So here it means automatically that Hadamard is applied to qubit 1 and identity is applied to qubit 2. State 0, 0. Okay. All right. So what is the outcome of this? We first apply H gate. So H gate, when applied to first qubit 0, it will give us 0 plus 1 over root 2. And then the second qubit is staying outside like this. So we can write E naught. This becomes 0, 0 plus 1, 0 by root 2. And now we operate C naught to 0, 0 and 1, 0. So C naught when operates on 0, 0, it gives us 0, 0 only. But C naught when operates on 1, 0, it gives us 1, 1. And this is nothing but an entangled state. And in fact, it's the Bell state. Bell state. And you know it is entangled because whenever the first qubit is 0, the second qubit will be 0. And whenever the first qubit will be 1, the second qubit will be 1. So we can know the status of second qubit, the status of one qubit just by measuring other, right? So we can know the status of one qubit by measuring the other. So you are basically doing a non-local operation. So you are not interacting with the qubit which you want to measure, but you are still able to know its status. Okay. So 0, 0 upon this Bell socket. So Bell socket. So this is often called as a Bell socket as well. Will give us this state 0, 0 plus 1, 1 by root 2. And then we can see what happens when we take 0, 1, 1, 0, and 1, 1. Okay, which kind of state it is. So let's go to our IBM Quantum Composer and see how the Bell socket would give us the result when it is operated to the basis states. So, okay, yeah. So first we'll see how, okay, I'll write it here. Bell socket or entangling socket. And we know that 0, 0, we just proved it, should give us 0, 0 plus 1, 1 by root 2, right? Let's see it. So our qubits are initialized in 0, 0 state. I apply a Hadamard gate to the first qubit, and then I apply a control NOT gate. This is a Bell socket. And we see our state is now 0, 0 and 1, 1 superposition. So 0, 0 plus 1, 1 by root 2. Next, we apply, let's say 0, 1. So to apply 0, 1, I'll do it here. So see, even though here it looks like Hadamard and not Git are operated at the same time, uh, it doesn't really matter. I mean, it's equivalent to saying, uh, this, then I'm putting a Hadamard Git here, and yeah, so we can differentiate the timestamps. All I'm trying to tell is this. Okay. So in this timestamp, we are first applying a control not, sorry, first applying a not gate to the second qubit, and then we are applying, this head mark to the first qubit, and after that we are applying a control not to both qubit, where first qubit is control and the second qubit is target. Okay, so when it is applied to 0, 1, what we are getting is 1, 0 and 0, 1. So now we are getting a state where it is 1, 0 plus 1, 0 plus 0, 1. 0, 1 by root 2. And this is when we are applying 0, 1, right? Yeah, 0, 1. Let's see, maybe I should enlarge this box. And how is this bell socket? This bell socket is Hadamard followed by a control not gate, right? Yeah. And then next we apply 1, 0. Okay, so yeah, I just wrote this thing 0, 1, 1, 0, 0, 1 over root 2. Next we see what happens when we apply 1, 0, right? So for applying 1, 0, what I do, I'll just simply put this C naught and put this not here and put it here and do this instead, right? Yeah. Okay, so now it is 1, 0, and for 1, 0, we see the state is becoming 0, 0 plus 1, 1 again. But now we see that the 1, 1 state has a phase of pi, so it would give a negative sign. So our state then becomes 0, 0 minus 1, 1 over root 2. And finally, we apply the state 1, 1 to the state to the entangling circuit. So we need to have another one here. Okay. And then we see we get 0, 1. Sorry, 1, 0. This is 1, 0 state, and this is 0, 1 state. But then the 1, 0 state has a minus sign because of this phase pi, just because of this phase pi, right? So I'll write it as 0, 1 minus 1, 0. So the state becomes 0, 1 minus, oops. Yeah, so the state becomes 0, 1 minus 1, 0. Sorry about that. 0, 1 minus 1, 0 over root 2. Oh. What's up? So we saw that we can create different bell states. So these are the different bell states: 0, 0 plus 1, 1 by root 2, 1, 0 plus 0, 1 by root 2, 0, 0 minus 1 by 1, 1 by root 2, and 0, 1 minus 1 by root 2. So these are the four bell states. People often write it using the following symbols. So some people write it like psi plus, this as psi minus, this as pi minus, and this as pi plus. So these are the four bell states, and they form a basis of their own. So what I can write is this: psi plus, psi minus, phi plus, phi minus forms a bell basis. So as per quantum mechanics, we can measure things in different bases, right? Even with quantum computing, we can measure things in different bases, and an important basis is Bell basis. Some other basis that we have seen, there was this computational basis, right? Computational basis, which is uh, measuring in 0, 1. If it is for 2 qubit, it is 0, 0, 1, 1, 0, 1, 1, 0. And then there is this Hadamard basis as well. Hadamard basis or diagonal basis, which is to measure in the plus minus states, where plus minus states are nothing but, plus is 0 plus 1 by root 2 and minus is 0 minus 1 by root 2. All right. So here in this tutorial, what we saw, just to summarize, we looked at how we can implement uh, quantum states. So in summary, we saw uh, how to implement different quantum states, which could be 0, 1, a plus state or a minus state. They are the basis states, right? They implement different states. How we can implement different quantum gates, both single qubit and 2 qubit gates. How we can implement or how we can verify circuit identities. And how we can uh, generate Bell states. And we saw how to do all those things here, right? These are 4 blocks. Again, these are for gates. This is for the circuit. So the circuit is composed of qubits and then gates putting on them on these qubit lines. We can see the probability distribution here, and here is the Q sphere that gives us information about the phase, right? The phase of the quantum state. And this is the coding part, and we did not touch upon it. It will be a different lesson sometime. But yeah, this is a first exposure to uh, quantum computing basics on IBM Quantum Composer platform. And I hope you could cook up your own circuit here. You could do some Bell measurements. You can also do the next step that can directly result from here. That is the teleportation. All right. So uh, that's it for the time being. And I hope you enjoyed this session and this would motivate you more for putting your hands on this IBM Quantum Composer platform. And also you can jump in to do some advanced circuits on this, just with this drag and drop. And if you're excited, then you can also do some programming on Qiskit to construct your own circuit and verify your own identities and implement some algorithms as well. So it was nice talking to you all. And I hope to create some more content and teach you guys more in the future. Bye bye.